Welcome to the deep dive. Now, if you're gearing up to become an aviation maintenance technician, you already know that some of the most critical parts of an aircraft, well, they're hidden from view.
That's right.
Today, we're essentially pulling back the floorboards, opening up the cowlings to really explore this complex, silent network that's the backbone of flight controls, engines, everything really.
Yeah.
Fluid lines and fittings.
Yep.
We're talking hydraulics, fuel, oil, even oxygen lines. It's pretty high-stakes stuff.
It absolutely is. And look, for you, the AMT student listening,
Yeah.
just knowing the basics about fluid lines, that's not going to cut it.
Right.
Failure in these systems, a leak, maybe catastrophic blowout or some other emergency, it almost never comes down to the line material failing on its own. It's usually procedural error. Someone picked the wrong line or didn't fabricate it quite right, or maybe installed it incorrectly, didn't torque it properly.
So human error,
Yeah.
essential.
Pretty much.
Yeah.
So our mission today really is to take that textbook knowledge you're getting about rigid tubing, flexible hoses, all those critical connectors, and turn it into absolute field-ready precision. That's the goal.
Okay, field-ready precision. I like that. So let's unpack this. We've got, broadly speaking, two main types of these conduits, right? Rigid tubing for the long, straight, stationary runs, and then flexible hoses where things move or vibrate a lot.
Exactly.
We should probably start with backbone, the rigid lines. And that means talking materials first, because the pressures involved, the type of fluid that dictates everything.
Okay, rigid lines, metal tubing. We're basically talking about three main families: aluminum alloys, steel, and titanium.
Right.
Aluminum alloys are kind of the workhorse. They're light, they're relatively easy to work with.
But not all aluminum is created equal, right? There's a definite hierarchy based on pressure. You can't just grab any old aluminum tube.
Absolutely not. No way. If you're dealing with really low pressures, negligible stuff, think instrument lines, maybe vent lines where it's just a channel.
Okay.
Then you go for the softer, very workable alloys. That's your 1100 H14, your 3003 H14. Easy to bend, easy to flare, but it just can't handle significant internal pressure.
Makes sense. So what happens when we step up to what you might call medium pressure? Those common systems, maybe 1,000, 1,500 PSI, standard hydraulics, pneumatics, fuel, oil lines.
Right. Now you need more strength. Significantly more tensile strength. So you're looking at alloys like 2024 T3, 50520, and 6661 T6.
That 2024 T3 seems pretty common.
It really is. Probably the most common you'll see in general aviation hydraulics. It's got a good balance of strength, corrosion resistance, and it's still reasonably light. And of course, those T3 or T6 designations tell you they're heat treated for extra strength.
Okay, so aluminum tops out around 1,500 PSI for these main applications. What about the heavy hitters? Systems pushing 3,000 PSI landing gear, flaps, brakes, and what if the line runs through a really risky area, like a fire zone, or maybe a wheel well where it could get hit by debris?
Now you're entering the realm of steel. Specifically, corrosion-resistant steel, CRES. We're talking grades like CRES 304, 321, or maybe CRES 304, 18 hard.
And steel is obviously much tougher.
Oh, yeah. Much harder to work with cutting, bending, it resists all that. But the trade-off is that dramatically higher tensile strength compared to aluminum.
And that strength leads to an interesting design choice, doesn't it? Regarding wall thickness.
It really does. Because steel is so much stronger, engineers can use steel tubing with much thinner walls to handle the same pressure.
Right.
And here's the fascinating part. When you compare the final installed weight thin-walled steel versus the thicker-walled aluminum you'd need for 3,000 PSI, they're often surprisingly comparable.
Huh. So you get the high-pressure capability, the FOD protection in places like the wheel well, without necessarily adding a huge weight penalty.
Exactly. Plus, for these high-stress, high-pressure applications, you typically don't use a standard flared connection with steel.
Right, the pressures are too high.
Way too high for a reliable long-term seal, especially with vibration. Steel tubing usually gets heavy-duty connections like swaged fittings, or the high-pressure standard, which is MS flareless fittings. We'll get into those specifics later.
Okay, so if steel handles 3,000 PSI, where does titanium 3AL 2.5V fit into this picture? Sounds like the next level up.
It is. Titanium is the sort of ultimate high-performance option. Very expensive, but incredibly strong and light. You see it a lot in modern transport aircraft, high-performance military jets. Anywhere systems run consistently above 1,500 PSI, and saving weight is absolutely critical.
How does it stack up against steel, numbers-wise?
Well, titanium 3AL 2.5V is roughly 30% stronger than steel, but, and this is amazing, it's about 50% lighter.
Wow, half the weight for more strength.
Precisely. It's really the peak of strength to weight for fluid lines. However, and this is a safety rule, every single AMT must have burned into their brain. There's one place titanium absolutely cannot go.
The oxygen system. Let's
Yeah.
make this crystal clear. Why is that?
Okay, listen up, because this is vital. Titanium and its alloys are highly oxygen reactive. They're what we call pyrophoric, meaning they can literally ignite spontaneously if they experience friction or heat in an oxygen-rich environment. So imagine you use a titanium tube or fitting in an oxygen system. If that line gets damaged internally, even a microscopic scratch, a tiny crack, anything that exposes a fresh metal surface, the heat from friction, maybe impact, combined with that pure, pressurized, gaseous oxygen, boom, spontaneous combustion.
Not just a leak, an explosion.
A violent reaction, massive energy release, immediate system failure, and a severe fire hazard. And this isn't just high pressure. It can happen even at lower oxygen pressures. So the rule is absolute. Use CRES, use certain aluminum alloys, but never, ever use titanium for oxygen lines or fittings.
That is definitely a life and death distinction.
Wow.
Okay, so when titanium is used safely, say in hydraulics, the fittings are specialized too, right? You mentioned cryofed or swaged.
Exactly. Because titanium is so hard and strong, you often need specialized connection methods that move beyond traditional flaring or even standard flareless fittings.
Makes sense. Now, speaking of identifying materials, once a line is installed, how do you tell what it is out in the field? You know, telling CRES from plain carbon steel just by looking isn't easy.
Right. Visual ID is unreliable. So we rely on clear, standardized markings. For larger diameter aluminum tubing, it's usually stamped directly with the alloy designation. You'll see 2024 T3 or something similar.
Okay. But what about smaller tubing?
For smaller aluminum tubing, the standard is color coding. You'll see painted bands near the ends, sometimes in the middle too. These bands aren't supposed to be more than 4 inches wide.
Okay, color codes. These are ones the learner definitely needs to nail down.
Absolutely. If you see a white band, that's your soft 1100 alloy. Green means 3003. Red indicates that common medium pressure alloy, 2024. And blue and yellow together.
That combination signifies 6061T6. And if there are 2 colors used, they just share that 4-inch bandwidth equally.
Got it. White, green, red, blue, yellow. Okay. Beyond the material itself, we have to talk about sizing. This often trips up new students because it's not like standard plumbing sizes.
No, it's specific to aviation. All aircraft fluid lines are sized by their outside diameter, the OD, and it's measured in 1/16ths of an inch.
So if someone says number 6 tubing, that means the OD is 616ths of an inch, which simplifies to 38ths.
Exactly. Or a number 12 tube is 1216ths, 3/4 of an inch OD. Simple enough.
But the OD isn't the whole story for flow, is it?
Not at all. You also absolutely need to know the wall thickness. That's usually printed or stamped on the tubing too, typically in thousandths of an inch.
Why is wall thickness so critical?
Because the actual flow capacity and the fluid velocity depend on the inside diameter, the ID. And you need the OD and the wall thickness to figure that out.
Okay, so how do you calculate the ID? It's simple math. You take the outside diameter and subtract twice the wall thickness. Remember the twice part? Because the wall exists on both sides of the diameter.
Right. Give us an example.
Okay, let's take a common one, say a number 10 tube, that's 116ths or 0.625 inches OD. Let's say the wall thickness printed on it is 0.063 inches.
Okay.
So the ID is 0.625 inches minus 2 times 0.625 minus 0.126, which gives you an ID of 0.499 inches.
Almost half an inch ID. And knowing that precise ID is crucial if you're replacing a section, right, to keep the flow dynamics correct.
Absolutely critical. You need to maintain the design flow characteristics of that system.
All right, so we've selected the right material and size. Now comes fabrication. The goal here is perfection, basically, because every tiny mistake, starting right from the initial cut, well, that's a potential leak or failure waiting to happen down the road.
That's the reality.
All right.
And a good habit is to cut the new tubing about 10% longer than the piece you're replacing. It just gives you a little bit of margin for error when you're doing the flaring and bending.
Good tip. So, the main goal when cutting.
A perfectly square end, 90 degrees, no angle. For softer metals like copper or aluminum, your standard tube cutter works fine. But there's a technique to it.
Don't just crank it down.
Exactly. Use only light pressure. Tighten it just a little bit with each rotation. Be patient.
What's the risk if you rush it, apply too much force?
2 big problems. First, you'll deform the tube wall, squeeze it inward. That can make flaring difficult or even impossible later. Second, you create huge burrs on the inside edge.
And those burrs are bad news.
Very bad. They restrict flow, obviously. They create turbulence. They act as stress risers, potential cracking points. And worse, tiny metal fragments can break off and contaminate the whole fluid system.
Okay, light pressure for soft metals. What about the hard stuff? CRES, that 6061 T6 aluminum, titanium.
Standard tube cutters often won't work well or might damage the tube. You really need specialized tools. Chipless cutters are ideal because they slice cleanly without generating debris.
What if you don't have a chipless cutter? Is a hacksaw okay?
It can be, but it's not ideal. If you must use a saw, choose a fine-tooth hacksaw, preferably 32 teeth per inch. And here's something counterintuitive. Using that fine blade actually reduces the amount of work hardening on these tough materials compared to a coarser saw.
Interesting. Okay, the cut is made, hopefully square. Now we get to what you called maybe the most critical small step and one that often gets messed up by beginners. Deburring.
It is absolutely vital and requires real care. You have to remove every trace of burr, both on the inside and the outside edge of the tube. You can use the edge of a sharp knife carefully, the little blade often found on the tube cutter itself, or a dedicated deburring tool.
What's the critical mistake to avoid during deburring?
Precision is key. You cannot, under any circumstances, allow the deburring tool to significantly thin, fracture, or chamfer the tube wall itself. You're just removing the burr, not reshaping the end of the tube.
Why is even a tiny bit of thinning there so bad?
Because that thin spot instantly becomes the weakest point of the entire cube end. When you go to flare it later, that weakness is exactly where the flare will crack or fracture.
Ah, so the flare itself fails.
Right. It won't seal properly, leading to persistent leaks. Or, under high pressure and vibration, it could just shear off completely. A correctly deburred tube end should look perfect, square, with full wall thickness right to the edge.
Okay, ends cut square, perfectly deburred. Now, bending. We already established bends are needed even if a straight path exists, right? For thermal expansion and vibration.
Exactly. A long, perfectly straight run of rigid tubing acts almost like a guitar string. It can resonate with engine vibration, amplify it, and eventually lead to fatigue cracks. Bends act like shock absorbers, soaking up that vibration and allowing for thermal expansion and contraction without stressing the fittings.
And the goal for the bend itself?
A smooth, consistent radius, no flattening, no kinking. For tubing under a 1/4 inch OD, you might be able to do it carefully by hand over a suitably sized form. But anything larger definitely requires a proper tubing bender.
And the bender has to match the tube size exactly.
Has to. Using the wrong size bender guarantees you'll flatten or kink the tube. For larger diameters or harder materials like CRES, you might even need a production bender, not just a hand tool.
Now, there's a specific limit on how much flattening is acceptable, isn't there?
Yes, the standard is quite clear. A small amount of flattening in the bend is usually okay. But the rule is, the smallest diameter measured across that flattened portion must not be less than 75% of the original outside diameter of the tube.
So if it flattens more than 25%, it's scrap.
It's scrap, no question. Same if the bend is wrinkled or has any kind of kink. That 75% rule ensures you maintain enough cross-sectional area for flow and enough structural integrity to handle the pressure.
Good rule to remember. And placement of the bend matters too, right? Near the fittings.
Yeah, you always want to start any bend a reasonable distance away from where the fitting will sit. You need enough straight tube length there to allow the sleeve and the nut of the fitting to slide back clear of the end during assembly or inspection.
Okay, now what about those? Let's call them field expedient bending methods. When you don't have the perfect bender, the sand filler method sounds pretty old school.
It is, but it can work in a pinch. You plug one end of the tube maybe with a wooden dowel or flatten it or even solder on a cap. Then you pack it absolutely tightly with fine, dry sand. Plug the other end.
So the sand acts like an internal support.
Exactly, like an internal die. It prevents the tube walls from collapsing inward or kinking as you carefully bend it around a forming block or a suitable radius.
What's the biggest danger with using sand?
Contamination, 100%. After the bend is made, you have got to ensure every single grain of sand is removed from inside that tube. Shake it, blow it out with compressed air, visually inspect it.
Because any leftover sand becomes...
Foreign object debris, FOD. It can jam valves, score cylinder walls, block tiny orifices in hydraulic components. It's a major hazard. If the line has complex bends, you might even need a bore scope to be sure it's perfectly clean.
Okay, high risk if not done meticulously. What about the fusible alloy method? Using that low melt point alloy.
It's generally cleaner, less risk of particulate contamination. The alloy typically melts around 160 degrees Fahrenheit, so just above boiling water temperature.
How does it work?
You fill the tube with the molten alloy, usually by immersing it in hot water. Let it cool and solidify. The solid alloy provides excellent internal support. You make your bend, then you put the tube back in hot water, the alloy melts, and you pour it out.
Seems straightforward, but there's a critical warning.
Absolutely critical. You must only use hot water to melt the alloy, both for filling and removal. Never use a torch, heat gun, or any other direct heat source.
Why not?
If you overheat that specific alloy, it undergoes a change. It can actually bond to the inside surface of the tubing. It becomes impossible to remove completely, and you've just ruined an expensive piece of tubing. Hot water only.
All right, fabrication's done, bending's complete. Now we get to the crucial part of preparing the tube ends for connection. And this is where we hit a fundamental difference between aircraft standards and, say, automotive work. This is absolutely mandatory knowledge for any AMT.
This is a big one, a really big one. It separates professional aviation practice from what you might see in a car repair shop. Aircraft fluid line flares must be angled between 35 and 37 degrees.
35 to 37 degrees, specifically.
Yes, and that specific, relatively shallow angle can only be produced by specialized aircraft flaring tools.
Okay, so why is the common 45-degree flare, the kind you find on tools at any hardware store, absolutely forbidden in aviation? What actually goes wrong if you use one?
It's about stress concentration. That steeper 45-degree angle creates a much sharper edge where the flare contacts the cone of the fitting. When you tighten the nut, all the force gets concentrated right on that thin edge.
Like a knife edge.
Essentially, yes. It creates an intense stress riser. Under system pressure and vibration, that flare is extremely prone to literally being cut off by the fitting or shearing away. Catastrophic failure potential.
Whereas the 35 to 37-degree flare
Distributes that clamping force over a much wider surface area on the fitting cone. It creates a strong, durable, reliable metal-to-metal seal that can withstand vibration and pressure cycles.
Okay, 35, 37 degrees it is. For softer metals like aluminum or copper, the standard is usually a single flare, right? And the tool often helps guide you.
Yes, the common rolling-type hand flaring tool is designed for single flares on softer materials. It typically has a flooring block to clamp the tube and a yoke with a flaring cone pin. Many are self-gauging,
Meaning
there's often a stop or a design feature that ensures you clamp the tubing at the correct height relative to the top of the die block. Usually it should be perfectly flush.
what happens if you clamp it too high or too low?
Too high, and the flare becomes too large in diameter. It might interfere with the threads on the fitting nut. Too low, and the flare is too small, too weak, and won't seal properly.
And here's a critical point you mentioned earlier. Never try to fix a bad flare by just cranking down harder on the nut.
Never. If the flare is crooked, cracked, undersized, oversized, over-torquing will not magically fix the seal. It will likely just damage the flare further or even damage the fitting itself. If the flare isn't perfect, you cut it off and do it again.
Okay, so that's single flaring. What about double flaring? Why the extra step of folding the tube end back on itself?
Double flaring is specifically required for soft aluminum alloy tubing that's 3/8 of an inch OD or smaller. It provides significantly enhanced durability, especially in high vibration environments.
How does it achieve that?
3 main reasons. First, by folding the material back, you literally double the thickness of the flared section. This makes it much more resistant to being cut or sheared by the tightening force of the nut.
Okay, makes sense. Stronger.
Second, that folded surface tends to be smoother and more perfectly concentric than a single flare, which generally leads to a better, more reliable seal against the fitting cone.
And third,
It offers much greater resistance to the shearing effect caused by high operating pressures combined with vibration. It just holds up better under stress.
So the process involves 2 stages with the tool.
Correct. Typically, you use an adapter insert first. This gently forms the tube end into a sort of bell shape. Then you remove the adapter and use the main flaring cone, which folds that bell back down onto the main tube body, creating the double thickness flare.
A bit more complex, but necessary for those smaller, softer aluminum lines.
Absolutely necessary for reliability in those applications.
Okay, so flaring is for connecting to specific fittings. What if we need to connect the rigid tube to a flexible hose? That's where beading comes in, right?
Exactly. Beading is used when you need to attach a flexible hose using a hose clamp. You typically see this in lower to medium pressure systems, maybe coolant lines, vacuum lines, instrument air sometimes.
And what does beading actually do?
It uses a tool to form a raised lip or ridge circumferentially around the end of the tube. This bead provides a positive stop for the hose and gives the clamp something substantial to grip onto, preventing the hose from slipping off under pressure.
What tools are used for beading?
There are hand beading tools, usually suitable for tube ODs from about a quarter inch up to an inch. For production work or larger sizes, machine beading rolls are used. You can even use grip dies for very small tubing.
Is there a trick to getting a good bead?
Lubrication is key. Always apply a light oil to both the inside and outside of the tube and before you start the beading process. This helps the metal to form smoothly and prevents the tooling from galling or damaging the tube surface as it forms the bead.
Okay, lines are fabricated, ends are prepped. Now, how do we actually connect everything together? This brings us to fittings. And understanding the difference between the two main types of threads used in aviation is really fundamental.
Absolutely. You've got pipe threads and you've got machine threads. They work completely differently, especially when it comes to sealing.
Let's start with pipe threads. What's their defining characteristic?
Taper. Pipe threads are tapered. The male thread gets slightly wider along its length, and the female thread gets slightly narrower. When you tighten them, the threads themselves wedge together.
So the threads themselves form the seal.
Correct. The interference fit between the tapered threads creates the seal. Because of this metal-on-metal wedging, though, they usually require some kind of sealant or lubricant.
To prevent galling and ensure a tight seal.
Exactly. You need an approved lubricant or thread sealant to fill any tiny imperfections and allow proper tightening without damaging the threads. But, and here we go again with the critical safety rule.
Oxygen systems.
Oxygen systems. You must never use any standard petroleum-based lubricant or sealant on oxygen fittings. Oxygen reacts violently, potentially explosively, with hydrocarbons like oil or grease.
So what do you use for oxygen pipe threads?
Only specialized oxygen-compatible lubricants or sealants, specifically approved for that use. Sometimes, certain types of dry seal pipe threads are used, which theoretically don't require sealant, but extreme care is always needed. Contaminating an oxygen system is incredibly dangerous.
Got it. Okay, that's pipe threads tapered, seal on the threads, need careful sealant selection. What about machine threads?
Machine threads are completely different. They have straight, parallel sides. There's no taper at all.
So they don't seal by themselves?
Not in the slightest. Their only purpose is mechanical, to draw components together, like screwing a nut onto a bolt or to hold a fitting securely in place through a bulkhead. The fluid sealing happens somewhere else.
How is the seal made then with machine threads?
It relies on a separate sealing mechanism. This could be the flare on the tube end pressing against the fitting cone, like we just discussed, or it could be a crush washer, a gasket, or a synthetic seal like an O-ring captured at a groove. The threads just provide the clamping force.
And the sizing for machine threads follows that dash number system we talked about for tubing.
Yes. Conveniently, the dash number on a machine thread fitting corresponds to the nominal OD of the tubing it's designed for, in 1/16 of an inch. A -8 fitting goes with -8 12-inch tubing.
Okay, let's dive into the two major fitting standards that use these machine threads for clamping. The classic and fittings.
An Army-Navy standard. These are the tried and true flared fittings. They're incredibly common, reliable for lower and medium pressures, relatively easy to assemble and disassemble. You'll find them everywhere.
Describe the components of an AN flared fitting connection.
It's basically two main parts plus the flare on the tube. You have the nut, which is an AN8 endpoint part number, and you have the sleeve, AN8 one time.
What does the sleeve do?
The sleeve is really important. It slides over the tubing behind the flare. Its main job is to support the tube right where it meets the flare, strengthening it against the stresses of vibration. Then the nut goes over the sleeve and threads onto the male fitting.
And tightening the nut does what?
It draws the flared end of the tube, supported by the sleeve, tightly against the 37-degree cone surface machined into the male fitting. That precise metal-to-metal contact between the flare and the cone creates the seal.
Simple and effective. And we identify the material of AN fittings by color, right?
That's the standard. Steel AN fittings are typically colored black. Aluminum alloy AN fittings are blue. And sometimes you'll see aluminum bronze fittings, often used in higher temperature areas like fire zones. Those are usually cadmium-plated, giving them a goldish look, or sometimes left natural.
And a crucial point. Unflared fittings look similar to MS flareless fittings at a glance, but they are absolutely not interchangeable.
Not at all. You can usually spot an AN fitting by the visible cone shape on the male end where the flare seats. MS fittings look different. Mixing them up could lead to leaks or connection failure.
Okay, that brings us neatly to MS military standard flareless fittings. What's their primary application?
High pressure. MS flareless fittings were specifically designed for 3,000 psi hydraulic systems. especially those subject to severe vibration and pressure surges, like landing gear or flight controls.
And the key difference is they eliminate the flare entirely.
Right. By getting rid of the flare, you eliminate what is often the weakest point in a traditional high-pressure connection.
So how does the MS fitting seal and hold without a flare? It relies on that sleeve again, but in a different way.
Exactly. The MS flareless system also uses a body, a sleeve, and a nut. But the MS sleeve is the critical component. It's made of hardened steel and has a precision-engineered cutting edge on its inside diameter.
A cutting edge.
Yes. When you tighten the nut correctly, this sharp edge is forced to physically bite into the outer surface of the tubing. This controlled bite creates both a mechanical lock, preventing the tube from pulling out, and a high-integrity metal-to-metal seal at the same time.
That sounds like it requires a very precise installation process.
It absolutely does. And it involves a mandatory step called presetting the sleeve onto the tube before you install it in the aircraft. You can't just assemble it loosely and tighten it down.
Okay, walk us through that presetting procedure. This sounds like a place where technicians could easily go wrong.
It is. Get this wrong, and the fitting will likely fail. First step, as always. Make sure the tube end is cut perfectly square and thoroughly deburred. Then, slide the nut onto the tube, followed by the sleeve, making sure the cutting edge of the sleeve faces the end of the tube.
Okay, nut, then sleeve.
Right. Now, you need a presetting tool, which is essentially a high-quality steel version of the fitting body, or you can use the actual fitting body if it's steel. Secure the presetting tool or fitting body firmly in a vise. Insert the tube end fully into the tool until it bottoms out.
Tube is bottomed. Now what?
Hand tighten the nut until you feel it start to snug up. Now here's the critical part. Continue tightening the nut with a wrench until you feel a sudden, significant increase in resistance. That indicates the cutting edge of the sleeve is fully engaged and started to bite into the tube. An alternative way to gauge this initial bite is to tighten until the tube no longer rotates within the fitting when you try to turn it by hand.
Okay, that's the initial bite set. What's the next step for the final preset torque?
It depends on the tubing. After that initial bite, you need to tighten the nut a specific number of turns. For aluminum alloy tubing that's 12-inch OD or smaller, you tighten it 1 full turn to 1 in 16 turns.
1 1/6 turns.
Correct. For steel tubing or for aluminum tubing larger than 12-inch OD, you need a bit more, 1 in 16 turns to 1 in 12 turns.
Okay, very specific rotation amounts. And after doing that, you need to check it.
Absolutely mandatory check. After presetting, you disassemble the fitting. Carefully inspect the tube where the sleeve bit into it. You should see a distinct, uniform indentation. Crucially, you must also check that the end of the tube extends slightly beyond the pilot portion of the sleeve. The required protrusion is typically between 332 and 1/18 of an inch.
Why is that protrusion so important?
If the tube end is flush with or recessed inside the sleeve pilot, it means the sleeve didn't bite deeply enough or the tube wasn't fully inserted. Under high pressure, that connection could literally blow apart. That protrusion confirms a proper grip.
Wow. Okay, so presetting is vital for MS flareless. Now, quickly, what about fittings designed to be totally permanent? Things like swaged fittings.
Right. These are for connections you don't plan on taking apart routinely. Swaged fittings, like the common Permaswade brand, are often used with CRES and titanium tubing, especially in complex or inaccessible areas.
How do they work? No threads involved.
No threads for sealing. You use portable hydraulic tooling that physically compresses or swages the fitting radially onto the outside of the tubing. It creates an incredibly strong, permanent, leak-proof, maintenance-free joint.
The downside being?
If you ever need to replace that section of tubing, you have to cut the swaged fitting off. There's no disassembly. So they're used strategically where long-term connection integrity outweighs the need for easy maintenance access.
We also saw Permalite mentioned.
Yeah, that's another type. Permalite works by axial swaging. It uses a tool to push a ring over the fitting, deforming the fitting material down into the tube surface. Similar permanent result, different mechanical action.
And then there's cryophyta. This sounds like something out of science fiction using shape memory alloys.
It really is clever material science. Cryophyte fittings are used a lot in modern transport aircraft hydraulic lines, especially with titanium tubing. They rely on a special nickel-titanium alloy sleeve, often called tenal, which exhibits shape memory.
Shape memory, meaning it remembers its original shape.
Exactly. The cryophyte sleeve is manufactured to be slightly smaller, maybe 3%, than the OD of the tube it's meant for. Then, it's cooled drastically, usually with liquid nitrogen. This extreme cold allows the sleeve to be temporarily expanded, maybe 5% larger than the tube OD.
So you have this super cooled expanded sleeve ready to go.
Right. While it's still freezing cold and expanded, you quickly slip it over the junction where two tube ends meet, or onto a tube and fitting end. As the sleeve rapidly warms up to ambient temperature over the next, say, 10–15 seconds,
It shrinks back.
it shrinks back with incredible force, trying to return to its original, smaller manufactured size. This contraction force is immense, far greater than you could achieve with wrench torque. It bites down hard onto the tubing, creating a super tight, permanent metal-to-metal seal. It's essentially a thermal lock, not a mechanical one.
Amazing. A fitting that tightens itself using temperature change.
Pretty neat stuff. Highly reliable in those demanding high-pressure, high-vibration environments.
Okay. We've got our properly fabricated line. We've chosen the right fitting type, AN flared, MS flareless, or maybe a permanent one. Now let's talk about the actual installation process, starting with the standard AN flared fittings. We know the seal is purely metal to metal.
That metal-to-metal contact is the whole principle, which leads to two absolute rules for installation. Rule number one, never put any kind of thread, compound, lubricant, or sealant on the flared face of the tube itself or on the cone surface of the male fitting.
Why not? Wouldn't lubricant help it seal?
Counterintuitively, no. It actually interferes. It prevents the clean, dry, metal-to-metal contact that's required for the seal to form correctly under pressure. It can trap debris or even mask a poorly formed flare, making you think it's sealed when it isn't. Lubricant only goes on the threads of the nut and the backside of the sleeve where it contacts the nut to ensure smooth tightening and prevent galling there.
Okay, keep the sealing surfaces clean and dry. What's rule number 2?
Alignment. The tube and the fitting must align perfectly before you start tightening the nut. Never, ever try to pull a misaligned tube into place by just cranking down on the fitting nut.
What happens if you force it?
You'll almost certainly damage the flare, maybe crack it or deform it, or you could damage the fitting cone. You're basically introducing stress into the connection before it even sees system pressure. If it doesn't line up naturally, the tube needs to be adjusted, maybe slightly rebent or replaced. Forcing it guarantees a future leak or failure.
Right, proper alignment, clean surfaces, now comes the tightening. For flared fittings, torque is everything, right?
Absolutely critical. You must use a torque wrench, and you must refer to the correct torque tables like the figure 920 mentioned in the prep guide. These tables give specific torque values, usually in inch-pounds, based on the tubing material, aluminum or steel, and the tubing size dash number.
Why is hitting that exact torque value so important?
It's a precise balance. Over-tightening will crush or fracture the flare, or damage the fitting threads. Under-tightening is just as bad. It won't create a proper seal, leading to leaks, or potentially allowing the fitting to vibrate loose and blow off under pressure.
So, guessing the torque by feel is a definite no-no.
Absolutely not. Using the correct torque value ensures the connection is tight enough to seal reliably, but not so tight that it damages the components. It also allows the fitting to potentially be disassembled and reassembled multiple times if needed and still seal correctly. Skipping the torque wrench is just asking for trouble.
Okay, torque is key for flared. Now, shifting to installing those MS flareless fittings after they've been properly preset. The tightening process here is different. It's based on rotation, not a specific torque value.
That's correct. Once the sleeve is properly preset onto the tube, the final installation tightening is done by feel and measured rotation. First, you insert the preset tube end into the actual fitting body it will connect to in the aircraft. Hand tighten the nut until you feel it make firm contact, basically, until it's finger tight against the fitting body.
Finger tight, then what?
Now, you use a wrench. From that finger tight position, you tighten the nut exactly 1/6 of a turn.
1/6. How do you judge that accurately?
The easiest way is to look at the hex flats on the nut. 1/6 of a turn is exactly the rotation needed to move from one flat to the next adjacent flat. So note the position of one flat, tighten until the next flat is in that same position. That's your initial installation tightness.
Okay, one flat, 1/6 turn after finger tight. What if, after installation and pressurizing the system, you find a slight leak at that MS fitting?
Okay, if and only if leakage occurs after the initial 1/6 turn tightening, the procedure allows for one additional tightening adjustment. You are permitted to tighten the nut an additional 1/6 of a turn. One more flat.
So a maximum total rotation of 1/3 of a turn, 2 flats from the original finger tight position.
Exactly. That 1/3 turn, 2 flats, is the absolute maximum permissible tightening for an MS flareless fitting during installation or leak troubleshooting.
Let's really emphasize this for the listener. Why is exceeding that total 1/3 turn limit so incredibly dangerous? What damage does it cause?
because tightening beyond that limit drives the hardened cutting edge of the sleeve too deeply into the tube wall. It essentially creates a deep groove, which acts as a severe stress riser.
Weakening the tube right at the fitting.
Precisely. It significantly weakens the tube wall right where it experiences the most vibration and stress. Over time, with normal aircraft operation, vibration will concentrate at that deep groove, fatigue the metal, and eventually cause the tube to crack and shear off completely at the fitting. This results in sudden, massive fluid loss and likely immediate failure of whatever system that line serves.
So if it still leaks after a total of 1/3 turn?
You stop. Do not tighten it further. The fitting or the tube end is likely damaged or was improperly preset. You must disassemble it, inspect carefully, and likely replace the faulty component, possibly the tube end and sleeve, or even the fitting body. Never exceed that 1/3 turn limit.
Crystal clear. Okay, moving on to troubleshooting existing lines. If a technician finds, say, a minor scratch or a nick on an installed aluminum alloy line, can it be repaired or does it need replacement?
There are limits. For aluminum alloy tubing, minor scratches or nicks are generally considered acceptable if they are not deeper than 10% of the tube's wall thickness.
Only 10%.
Yes. And importantly, the damage must not be in the heel, the inside curve of a bend, as that's a high-stress area. The damage is within that 10% depth limit and not in a bend heel. You can often repair it by carefully smoothing it out with a burnishing tool to remove the sharp edges of the scratch, which act as stress risers.
What about steel or titanium lines? Same 10% rule.
Generally, no. CRES and titanium rely heavily on their surface condition for strength and corrosion resistance. Their limits for surface damage are usually much, much tighter. Often, any scratch or nick might require replacement. You absolutely must consult the specific aircraft maintenance manual for the repair limits on steel and titanium tubing. Never assume the 10% rule applies. Burnishing is often prohibited on these materials.
Good caution. What about dents in tubing? How much of a dent is okay?
Again, there are limits. Generally, a dent is acceptable if its depth is less than 20% of the tube's outside diameter. So a dent pushing in less than 1/5 of the way across is usually okay.
Any exceptions?
Yes, the big exception is, again, the heel of a bend. Dents located on the inside radius of a bend are not acceptable, regardless of depth, because they significantly weaken the tube structure in that high-stress area.
Can minor dents be removed sometimes?
There is a technique, though it's used cautiously. For minor dents, within the 20% limit, not in a bend, you can sometimes use what's called a bullet. This is usually a steel ball bearing or a slug of hard metal with a diameter slightly smaller than the tube's ID. You attach cable or use a dowel rod to carefully draw or push this bullet through the dented section of the tube.
And it sort of pushes the dent back out.
It helps to reform the tube closer to its original round shape, improving flow and reducing the stress concentration caused by the dent. But it's only for minor dents.
If the damage is severe, deeper scratches, bigger dents, cracks, damage in a bend, what's the repair procedure?
You have to cut out the damaged section completely. Then you insert a new piece of tubing. This new section must be of the exact same material, same outside diameter, and same wall thickness as the original line.
And how do you connect the new piece in?
You use standard fittings. For lower pressure lines or aluminum, you typically flare the ends of the existing tube and the new section and connect them using a standard AN union fitting, which is like a double-ended male fitting, along with the usual sleeves and nuts. For high-pressure lines like CRES or titanium, or sometimes for 6061T6 aluminum, you would likely use approved swaged fittings to permanently join the new section in place.
Makes sense. Cut out the bad, splice in the identical good using approved fittings. Finally, let's quickly touch on line identification again. Those tapes and decals are crucial for maintenance safety.
Absolutely vital.
Yeah.
You need to know instantly what's inside that line and what hazards might be associated with it. The standard system uses a combination of color codes, printed words like fuel, oil, hydraulic, and geometric symbols.
What do the symbols indicate?
They primarily identify the function or hazard. For example, a line carrying flammable fluid like fuel might have flam printed and potentially a specific symbol. Toxic materials might be marked toxic. Physically dangerous materials like high-pressure oxygen or nitrogen or very cold fluids are often marked PHDN, physical danger.
And where are these markers placed?
The standard is pretty thorough. You need identification markers near both ends of the line segment. You need at least one marker visible within each compartment the line passes through. And you need markers placed adjacent to critical components like valves, pumps, filters, etc.
What about in engine compartments where tapes might come loose?
Good point. In high-temperature areas or places where a loose cape could become a FOD hazard, like inside engine nacelles, the identification markings are usually applied directly using durable, heat-resistant paint instead of adhesive takes or decals.
Okay, we've thoroughly covered the rigid lines. Now let's switch gears to their flexible counterparts. Hoses. When do we typically need to use a flexible hose instead of rigid tubing?
There are three main scenarios. First, obviously connecting parts that move relative to each other. Think landing gear struts compressing, flight control actuators moving, or engine components shifting slightly on their mounts due to vibration.
Makes sense. Movement needs flexibility.
Second, in locations subject to intense vibration where even a bent rigid line might fatigue too quickly. A flexible hose can absorb more of that vibration. And third, sometimes they're just used as convenient connectors between segments of rigid tubing, perhaps to simplify installation or removal of components.
Now, just like with rigid lines, material selection is critical for hoses, but here it's all about chemical compatibility with the fluid inside, right?
Compatibility is absolutely everything. The inner tube of the hose is typically made from synthetic rubber or plastic. If you put the wrong fluid in contact with it, that fluid can literally dissolve or degrade the inner liner from the inside out, leading to contamination, leaks, and eventual rupture.
So matching the hose material to the system fluid is non-negotiable. Let's break down the common synthetic materials and what they're good for.
Okay? If your system uses standard petroleum-based products, that's things like jet fuel, aviation gasoline, avgas, or mineral oil-based hydraulic fluids, the common choices are Buna-N or neoprene.
Buna-N versus neoprene.
Buna-N generally has excellent resistance to those petroleum products. Neoprene also works, and it offers pretty good abrasion resistance on the outside, but its resistance to petroleum fluids isn't considered quite as good as Buna-N's.
Okay, so Buna-N or neoprene for petroleum, but what about the big one in commercial aviation hydraulics, that synthetic phosphate ester fluid, Skydrol?
Ah, Skydrol. That's a completely different animal chemically. If you expose Buna-N or neoprene to Skydrol, they will swell up, get gummy, and degrade very quickly. It's a guaranteed failure.
So what material do you use for Skydrol systems?
The go-to material is butyl rubber. Butyl is specifically formulated to be compatible with phosphate ester fluids like Skydrol. However, the reverse is also true. Butyl is not compatible with petroleum products, so you absolutely cannot mix them up.
Use the wrong hose, the system fails. Simple as that.
Pretty much immediate failure, yes. And hoses specifically approved for Skydrol will always be clearly marked off with the word Skydrol or a specific marking indicating phosphate ester fluid compatibility. We have to check.
Is there a material that works with pretty much everything?
Yes, the high-performance, high-cost option is Teflon, or PTFE, polytetrafluoroethylene. Teflon hoses are compatible with almost every fluid used in aircraft fuel, oil, Skydrol, coolants, you name it.
What are the other advantages of Teflon?
It has a much wider operating temperature range than most synthetic rubbers, typically from about -65 degrees Fahrenheit up to plus 450 degrees Fahrenheit. It also experiences less volumetric expansion under pressure, which can mean slightly better system response time. And a big plus, Teflon doesn't really degrade over time, so it has a practically unlimited shelf life, whereas rubber hoses do age and have expiration dates.
Okay, so Teflon is the premium versatile choice. Now let's talk about hose construction and how that relates to pressure.
Right. A typical hose has that seamless inner tube made of the compatible synthetic material we just discussed. Then, over that, there's one or more layers of reinforcement braid. And finally, an outer cover for protection against abrasion and the environment. The type and number of braid layers determine the pressure rating.
So what defines low, medium, and high pressure hoses?
Low pressure hoses, generally rated for systems below 250 psi, usually just have a fabric braid reinforcement, maybe cotton or synthetic fiber.
Okay, medium pressure.
Medium pressure hoses can typically handle pressures up to 3,000 psi in smaller sizes, though the pressure rating often drops to around 1,500 psi for larger diameter medium pressure hoses. These almost always use a single layer of woven wire braid, usually stainless steel, for reinforcement.
And high pressure.
High pressure hoses are designed to handle 3,000 psi reliably across all available sizes. To achieve this, they typically incorporate multiple layers of wire braid reinforcement.
More wire means more strength. Got it. How is hose sizing indicated? Does it use the same dash number system as rigid tubing?
Yes, conveniently it does. Flexible hoses are identified by a dash number stenciled right onto the side of the hose. This dash number directly corresponds to the size of the rigid tubing it's designed to connect to.
So a 9 of 6 hose connects to a 9 of 6 38-inch tube or fitting, the number doesn't actually tell you the hose's ID or OD directly.
Correct. It purely indicates compatibility with the equivalent rigid tube size. This makes matching components much easier during maintenance.
Okay. Now, installation. This seems like another area where small mistakes can have big consequences. You mentioned two golden rules earlier. Slack and twist. Let's start with slack.
Absolutely crucial. You must always install a flexible hose with some slack or a gentle bend. The standard recommendations is to allow for about 5 to 8% of the hose's total length as slack.
Why is that slack so important? What happens if you install it perfectly taut?
Because hoses behave counterintuitively under pressure. When a flexible hose is pressurized internally, the reinforcement braid causes it to actually contract slightly in length while expanding slightly in diameter.
It gets shorter when pressurized.
Yes, so if you install it completely straight and tight between two fixed points, when the system pressurizes, that contraction puts immense tensile strain on the hose and its end fittings. It will fatigue very quickly and eventually pull the fitting loose or rupture the hose. That 5–8% slack accommodates this natural contraction.
Okay, always allow for slack. Now, the second rule, avoiding twist. How do you ensure a hose isn't twisted during installation, and why is twist so bad?
Twisting a hose, even by just a few degrees, severely compromises the integrity of those reinforcement braid layers. It misaligns the weave, creating weak spots. Under high pressure, a twisted hose is far more likely to rupture or blow a fitting off.
So how do you check for twist?
You use the ley line. Most aircraft hoses have a continuous linear stripe printed or molded along their entire length.
Yeah.
This line should run straight along the hose when installed. It should not spiral around the hose.
The ley line looks like a candy cane stripe.
It's twisted. You absolutely must loosen the fittings and correct it before pressurizing the system. Many hose end fittings incorporate swivel nuts specifically to help eliminate twist during installation.
Good visual check. Any other installation considerations for hoses that flex a lot in service?
Yes. If a hose is expected to undergo repeated flexing motion, you need to ensure that the hose remains relatively straight for at least 2 hose diameters worth of length coming away from the end fitting.
Why is that straight section near the fitting important?
It prevents the flexing motion from concentrating all its stress right at the point where the hose joins the rigid fitting. Allowing that straight section distributes the flex more evenly along the hose body, dramatically increasing its service life.
Makes sense. Okay, finally, let's talk about clamping and supporting these hoses.
Hoses need to be properly supported to prevent chafing and excessive movement. The general rule is they should be secured with clamps at least every 24 inches, although often closer support is better, especially in high vibration areas.
What about tightening the clamps that secure the hose to a beaded tube or a fitting nipple, like a standard hose clamp? Are there torque rules there too?
Yes, and over-tightening is a common mistake that can damage the hose. For initial installation, it's best to use a torque limiting wrench calibrated for hose clamps. Values like 15 or 25 inch-pounds are common. Check the manual. If you don't have one, the manual often provides a finger tight plus turns method. Finger tight plus 14 turn.
What about checking clamps in service if you find one a bit loose?
It depends. For a standard non-self-sealing hose clamp, the rule is generally, don't disturb it if it feels reasonably snug, like finger tight, unless it's actually leaking. If it is leaking, you can tighten it slightly, usually no more than about 1/4 turn.
And for self-sealing hose clamps?
Those are designed to maintain tension. If you find a self-sealing clamp that's looser than finger tight, the procedure is usually to tighten it to finger tight and then add 1 additional 1/4 turn. But again, never exceed the specified tightening limits as you risk cutting into or crushing the hose underneath.
Okay. And the clamps used to support the hose along its run. The cushion clamps, there's an important distinction there too, especially regarding electrical bonding.
Yes, very important. You'll see rubber cushioned clamps, often called Adel clamps, which provide good vibration damping. You'll also see Teflon cushioned clamps, which are used where resistance to fluid like Skydroll or fuel is needed, although they offer a bit less vibration damping than rubber.
What's the critical rule about bonded clamps?
Bonded clamps have a metal strap embedded in the cushion that makes electrical contact with the clamp body. These are specifically designed for use on metal fluid lines, hydraulic, fuel, oil, to provide electrical bonding, preventing static electricity buildup. You must only use bonded clamps for these conductive fluid lines, and you often need to remove any paint or anodizing from the tubing where the clamp makes contact to ensure a good bond.
And unbonded clamps.
Unbonded clamps, which lack that conductive strap, are generally reserved for supporting non-conductive things, primarily wiring harnesses. Using the wrong type of clamp can compromise electrical bonding safety.
We're nearing the end here. We've fabricated, installed, and supported our lines and hoses. But before a flexible hose assembly, especially one you fabricated yourself by attaching fittings, can be put into service, it needs to be proof tested, right?
Absolutely mandatory. Every flexible hose assembly must be proof tested after fabrication or re-ending. This verifies the integrity of the hose material itself and, crucially, the security of the end fitting attachments.
What's the standard pressure requirement for this proof test?
It's typically tested to at least 1.5 times the normal operating pressure of the system it's going into. Some specifications might require twice the operating pressure, so always check the manual. This ensures it can handle pressure surges and has a safety margin.
And what fluid do you use for the test? Does it depend on what the hose will carry?
Yes. If the hose is for a hydraulic or fuel system, you typically test it using an approved hydraulic fluid or sometimes even clean water. If it's an air or instrument line hose, you test it using dry, oil-free compressed air or nitrogen.
There's a critical safety difference between testing with liquid versus gas, isn't there? Gas under pressure stores a lot more energy.
A huge difference, yes. Compressed gas stores a massive amount of potential energy. If a fitting fails during a high-pressure gas test, it can release that energy explosively, sending shrapnel flying. It's extremely dangerous.
So how do you safely conduct a proof test using air or nitrogen?
The standard safety procedure is to conduct the entire test underwater. You submerge the pressurized hose assembly completely in a tank of water. If there are any leaks, even tiny ones, you'll see a stream of bubbles, allowing safe detection. If a fitting were to fail catastrophically, the water absorbs most of the energy, making it much safer.
And when testing with liquids like oil or water?
The main precaution there is to ensure all trapped air is bled out of the hose assembly before applying pressure. Trapped air pockets in a liquid test can still compress and cause violent fitting ejection if a failure occurs, though not as severe as a pure gas test. Bleed it thoroughly first.
Good safety practices. One last point about some specific hose types. Preformed hoses. You see these sometimes, especially with Teflon.
Yes, particularly some medium-pressure Teflon hose assemblies are manufactured with specific permanent bends already formed into them. This is often done to allow the hose to snake around obstructions in very tight spaces, like engine compartments, without needing excessively sharp, stressed bends during installation.
What's the absolute rule regarding these preformed assemblies?
Simple. Never attempt to straighten out a preformed hose assembly. Trying to force it straight will damage the internal braid structure and permanently compromise the integrity of the hose. It defeats the whole purpose of the preforming and creates a weak spot. Install it as it was designed.
Makes sense. Don't fight the shave. Okay, we have covered a massive amount of detail here, from the millimeter precision needed for deburring to the immense forces in 3,000 psi systems and the chemistry of hose compatibility. If you had to boil it down, what's the single most important takeaway for that AMT student listening?
It's understanding that none of these rules, the 35 to 37 degree flare angle, the maximum 1/3 turn tightening on an MS fitting, the 5 to 8% slack requirement for flexible hoses, checking material compatibility, none of these are just arbitrary bureaucratic standards.
They come from somewhere.
They come from hard lessons learned, often from investigating failures, sometimes catastrophic ones.
Yeah.
They represent real engineering limits. Every time you ignore one of these details or cut a corner or guess at a torque value, you're potentially installing a hidden defect, a ticking clock, into a system that people's lives depend on. Precision, attention to detail. It isn't just preferable. It's the absolute prerequisite for ensuring the integrity and safety of that aircraft's fluid systems.
That really drives the point home. Precision is prerequisite. Okay, so we've recapped the critical skills. Selecting the right material, remembering that vital titanium oxygen warning, mastering the 35-37 degree flare, understanding the MS flareless presetting and the 1/3 turn limit, and ensuring slack and zero twist for hoses.
And we saw how technology is evolving, from the brute force of tightening a nut to the cleverness of the MS fittings vite, and even the material science magic of CryoFit's thermal lock.
All right, so here's a final thought for you, our listener, to maybe chew on after this. We just talked about CryoFit using a shape memory alloy, tinel, to create a seal through temperature change, moving beyond pure mechanics. If material science is already doing that, what's next?
Think about it. We're seeing research into things like self-healing polymers for fuel tanks. Could we one day see fluid lines made of materials that can repair minor leaks themselves? Or perhaps materials that actively adapt their properties based on pressure changes? Maybe seals that rely on magnetic fields instead of compression.
So the provocative thought is, If you were designing the fluid systems for an aircraft 10 years from now, aiming to eliminate leaks entirely, what emerging field of materials science or physics might you leverage? How could you move beyond the traditional flare, thread, and torque?
The future really depends on maintenance professionals like you, not just following the rules, but understanding the science behind the rules and being ready to adapt as technology continues to challenge those traditional mechanical assumptions. It's about looking beyond the current textbook.
Excellent point to end on. Thanks for taking this deep dive with us into the critical world of aircraft fluid lines and fittings. We hope this helps you build that field-ready precision. We'll catch you next time.